Welcome back. In the last lecture, we defined the dot product or the scalar product between two vectors. In this lecture, we will see very important use of the scalar product, which I mentioned in the last lecture, the vector projection. Let's take a look at two non-zero vectors u and v. The projection of the vector u on vector v is defined as the vector that points in the direction of v and has the magnitude given by the shadow cast by u. The projection vector is parallel to the vector v. These are three steps to find the vector projection in vector v direction, in the v direction. First of all, we find the unit vector in the v direction. The unit vector is equal to the vector divided by its magnitude, as we learned before. In the next step, we will use the dot product between u and v to find the length along the unit vector. And in the last step, we will multiply the magnitude of the projection, which is the second step, by the unit vector in the direction of v vector. We can write the expression for the projection vector in a different way. Let's see it together. We saw that the unit vector, that the projection vector for u on v is equal to the magnitude of the projection vector multiplied by the unit vector in the v direction, and it's equal to the dot product between the vector u and the unit vector of v multiplied by the unit vector v. But we also know that the unit vector in the v direction is, as we saw before, it's equal to the vector v divided by the magnitude of the vector v. Let's substitute it in the first equation here, and it's equal to the vector u multiplied by the vector v divided by the magnitude of vector v multiplied by, again, vector v multiplied by divided by the magnitude of vector v, and this is equal to the vector u multiplied by the vector v divided by the magnitude of vector v squared, all of this multiplied by vector v. It's another way to see the projection on vector v. So it's equal to the dot product between u and v multiplied by the magnitude of vector v squared, all of this multiplied by vector v. And in this expression, we don't have to find the unit vector in the v direction, and of course it's equal to the first equation here. So what we see here, let's recap the u and v vectors. If we see that this is u, if we say that this is u vector and this is the v vector, and this is the angle between them, so this one is the projection of vector u and vector v. It's like that, and this vector here we can call it u, that it's orthogonal to the vector v. And here we can see that from the vector addition on the first section, that the vector u is actually equals to the vector to the projection of vector u and vector v plus the vector that it's orthogonal to the vector v, and we call this thing here the vector decomposition. U is equal to the parallel component of vector u plus the orthogonal component of vector u. And this is a very, very important idea here to just decompose the vector into two components, the orthogonal one and the parallel one. That's it for now. See you at the next one.